Welcome to This Explainer. Today, we're doing something incredibly cool. We're unlocking the literal physics hidden inside mechanical firearms. We're going to break down exactly what happens in those tiny milliseconds between pulling a trigger and a projectile achieving precise, long-distance flight. And specifically, we're going to focus on the absolutely vital science of projectile rotation. So let's just dive right in. A fraction of a second reveals infinite physics. I mean, think about it. The entire sequence we're exploring today happens in a split second. To the naked eye, it's just a single loud bang, right? But if we metaphorically freeze time and stretch that fraction of a second out, we uncover this fascinating hidden world of extreme pressure and mechanical precision that dictates exactly where that projectile is going to end up.
Okay, let's dive into this with Section 1, the spark of ignition, from mechanical strike to chemical expansion. So picture this. It all starts in a state of tense rest inside the brass cartridge, which is basically a highly engineered pressure vessel. Step 1, the mechanical firing pin slams into the primer right at the base of the cartridge. Step 2, that violent impact creates a concentrated spark. And Step 3, that spark meets the gunpowder. Now, the powder doesn't just casually burn, it rapidly expands into a high-pressure gas. Because it's completely confined in this incredibly tight space, the kinetic energy literally builds exponentially in mere microseconds. It's an absolute pressure cooker.
Which brings us to Section 2, inside the rifled barrel, the journey of the copper-jacketed bullet. All that rapidly expanding gas we just talked about, well, it has to escape somewhere, right? And it does that by violently forcing the copper-jacketed bullet down the narrow corridor of the barrel. But actually, this introduces a massive mechanical hurdle. You have a small piece of metal being shoved through a tube by a completely chaotic explosion. If it just popped out the end like that, there is no way it would fly straight. It would immediately start tumbling wildly through the air. So how does a projectile achieve stability in flight? How on earth do we tame that massive forward momentum so the bullet flies perfectly straight?
Now, this brings us perfectly into Section 3, the science of spinning, the ultimate solution to projectile instability.
The answer is all about rifling. If you don't know what that is, rifling refers to the spiral grooves carefully machined directly into the inside walls of the metallic barrel. As the bullet gets violently pushed forward, the relatively soft copper jacket is physically forced to grip onto these super hard grooves. This highly engineered internal geometry forces the bullet to spin rapidly on its own axis before it ever leaves the gun. And this rapid rotation creates what we call gyroscopic stability. It relies on the conservation of angular momentum to keep the bullet flying point first. It's honestly exactly like a perfectly thrown spiral football.
And this brilliantly illustrates the duality of ballistic mechanics. On one side, you have the expanding gas. This is our chaotic, high-pressure pushing force. It's just pure speed and raw power. But, as we know, power without control is completely useless. So on the other side, you have the spiral rifling grooves. That's our guiding, stabilizing, rotational force. The barrel is basically acting as this crucial mediator. It takes that chaotic explosive energy and meticulously channels it through geometric precision, translating all that raw chaos into a perfectly stabilized, rotating trajectory. It's a real game changer.
Let's move on and see how this builds in Section 4, trajectory and physics. Out into the laboratory.
The moment that highly stabilized bullet violently exits the barrel into the open air, the mechanical journey ends and the aerodynamic journey officially begins. Accompanied by a sharp muzzle flash and a small cloud of escaping gas, the projectile's flight path is now dictated purely by physics. We can literally use real-time physics equations to calculate its exact trajectory midair. And here is the key takeaway. Because of that rapid spin induced by the rifling, those equations yield a perfectly stable, highly predictable flight path through space.
Which leaves us with a final, really fascinating thought to ponder. We've just seen exactly how spiral grooves perfectly stabilize a projectile to create a true trajectory. But what happens if we change the variables? How might altering the rotational spin completely rewrite the equations of this bullet's flight path? If the spin was faster, or slower, or engineered differently, how exactly would that alter the physics of its journey? It's a fantastic question, and it really opens the door to the most advanced levels of ballistic science.